Hello, I'm Norman Wildberger. This is going to be our last lecture for this first half of this course in linear algebra. Today I want to go over a topic that we visited a number of times, the idea of changing basis in a vector space, where we have not just one basis, but we have two bases, and we can describe a vector in the space either in terms of this basis or in terms of that basis. And the question is, how do we go back and forth from these two different points of view? In fact, this goes right back to our very first lecture in the subject, and we're going to revisit some of the examples that we looked at in that first lecture. So I want to formalize this business of change of basis, and I want to do it in a rather novel way. So there's going to be some aspects of this course which are novel even if you have studied or perhaps even taught linear algebra for many years. I then want to apply this change of basis framework to the important issue of Taylor coefficient vectors. So we're going to move into calculus just a little bit and extend some of the considerations that we had last time when we were talking about cubic splines. All right, so let's go back to our first lecture in this series where we had Bob and Rachel, and they both had affine systems to describe things happening in the plane. So Bob had two basis vectors which looked roughly like this. There was one pointing in this direction and another one pointing in this direction, and we called them E1 and E2. So when we were talking about Bob's system, we introduced not just these two vectors, but also a corresponding affine grid. So we looked at lines that we can draw equally spaced parallel to the two vectors, making a grid. And then there was Rachel's basis vectors, which looked something like this. It was F1 and F2, and she had a corresponding grid of lines made parallel to these vectors. What we're going to do today is we're going to look at both of them from a third point of view. Let's say our point of view. So we're going to introduce a new framework. We'll call the X and Y, spaced like this. So there's an X direction, there's a Y direction with coordinates 1, 2, 3, 4, 1, 2, 3, 4, and so on. So in our framework, we can say, Bob's basis vector E1 is actually the vector 2, 0. And the vector E2 is minus 1, 2. And we can look at Rachel's basis vectors, say F1, and say, well, that's roughly 5, 2. And F2, this one here, is 0, 4. So this gives us a way of objectively, concretely specifying what these four vectors are from an external point of view. All right, so some relations that we wrote down in that first lecture, and you might want to review that first lecture while in Alg number 1. We saw that F1 and F2 can be written in terms of E1 and E2. So for example, F1 is 3 times E1 plus E2. We can see that geometrically. If we take E1 there, then 2E1 will be out to here, and 3E1 will be out to here. And then if we add E2, well, then we get F1. Or algebraically, we can say that 3 times this one plus this one will give us 5, 2. And similarly, F2 can be expressed as E1 plus 2 times E2. There would be 1, and there would be 2. Algebraically, if we take E1 and we add 2 times this, well, then we can get 0, 4, which is F2. Okay, and then we were interested in the connection of how do we express another vector in the space, both in terms of Bob's system and in terms of Rachel's system. So we took another vector, and let's look at this one here, the same one respectively that we looked at before. Let's call it V. And now in our system, this is the vector 10, 8. 10 in this direction, 8 in this direction. So 10, 8, this vector V, can be expressed as 7 times this one plus 4 times this one. You can check that. Or it can also be expressed in terms of Rachel's vectors as 2 times this one plus this one. So we have this relation between the expression for V in terms of Bob and the expression for V in terms of Rachel. So a little bit more generally, we found an equation like this that relates the coordinates of a vector in Rachel's system with the coordinates of that same vector in Bob's system. So for example, this vector V, 10, 8, can be expressed as 7, 4 in Bob's system and 2, 1 in Rachel's system. So if we put an x1 equals 2 and an x2 equals 1, then 2, 1 in Rachel's system is equal to 7, 4 in Bob's system. Just reflecting the relationship here. All right, so what we want to do today is we want to look at this in a somewhat more systematic framework now. We've had more experience with vectors and matrices and so on, so I want to reformulate this and lay it out for you in a somewhat novel way. Let's make the observation that there are actually two different kinds of linear relations on that previous slide. There's the linear relation between the basis vectors themselves, between Bob's basis vectors E1, E2, and Rachel's basis vectors F1 and F2. So over here we have a relation which is between vectors. On the other hand, we had the relation between coefficients. So we said that if we had a vector V, then its coordinates in Rachel's system and its coordinates in Bob's system were related by this equation. The y1 is 3x1 plus x2, and the y2 is equal to x1 plus 2x2. So this expresses a relation between vectors, while this expresses a relation between coefficients. There's something of a duality here. Very similar, but actually different. Now, with our matrix formulation of things, we can try to encode both of these relations in a matrix form. Let's do this one first. So we're going to just write this the following way. We'll think of this coefficient vector, y1, y2, as a row. And here the coefficient vector x1, x2 as a row. And the connection between them is that we're multiplying this one on the right by the matrix 3, 1, 1, 2. Let's check that this equation is really the same as this one. So the first entry here, y1, is the first entry on this side, which is the product of this row times this column. 3x1 plus 1 times x2. That's exactly that equation. And y2 is the second entry, which is x1 times 1 plus x2 times 2. x1 plus 2x2. So this equation involving matrices encodes exactly this relation between the coefficient vectors in Bob and Rachel's system. Now over here we can express this relation also in a similar way. But I'm going to do it in a slightly different way by writing the vector F1 and F2 here as a column and writing this vector E1 and E2 as a column. So this encodes the same thing here because the top entry, F1, is 3E1 plus E2. And the second entry, F2, is 1E1 plus 2E2, right there. So we have these two matrix equations representing these two relations. But there is a big difference between these two equations. What's the difference? This is actually a familiar one. It fits into the framework that we've established so far because these are matrices or vectors with entries which are numbers. Those are the kinds of objects we've been dealing with so far. But over here, if we look at this carefully, we see that in fact the entries here are not numbers. They are themselves, in this case, vectors. So this kind of equation, even though it looks a lot like this equation, is actually of a fundamentally different kind. It's of a relationship between a vector of vectors and another vector of vectors with this matrix of numbers multiplying this vector of vectors. So this is something of a new framework, and we really ought to establish some new terminology to cover this situation. We shouldn't pretend that this is exactly the same as this, because it's not. It's fundamentally different. Now, for those of you who've had some physics training, the physicists distinguish between so-called covariant and contravariant points of view. Okay? What we're doing is we are going in that direction, but using sort of a different framework here. But it's roughly very analogous to that. So we need to introduce a new notation to cover this kind of relation. So let me remind you that the matrix algebra that we've been building up so far generally always involves numbers. So when we have a vector like this times a matrix like this, let me remind you the way that goes in general. So AB times X, Y, Z, W, then we get another vector of the same size as this one. This is really a 1 by 2 matrix followed by a 2 by 2, which gives us a 1 by 2. And the entry here is AX plus BZ and AY plus BW. On the other hand, we could multiply a matrix by a column vector on the right to get another column vector, and then we get AX plus BY first entry and CX plus DY the second entry. So usually all of these letters involved here are numbers. They're representing numbers. But here's the important, very simple observation, that this algebra also works if A, B, C, and D are numbers and X, Y, Z, and W are vectors. Because suppose that X, Y, and Z, W are vectors and A and B and C and D are numbers. Then this expression here, what does it consist of? So then AX plus BZ is another vector. We're taking a linear combination of the vectors X and Z. And here's another vector combination. So what we have is that this matrix of numbers times this matrix of vectors gives us a matrix of vectors. And similarly the other way around, if these things are all numbers and X and Y happen to be vectors, then these things are also vectors because they're linear combinations of vectors, so also vectors. So on the right hand side again we get a vector whose entries are vectors. And the argument is of course symmetrical, so it also works vice versa. If the A, B, and C, and D's happen to be vectors and the X, Y, Z, and W happen to be numbers, then we would also still get a consistent kind of augmented matrix algebra. So this may seem a little bit strange, and this is not done in traditional linear algebra courses, but we're going to see that it's actually a quite useful way of thinking. We're extending our thinking a little bit, and it's a useful and interesting extension. All right, we are now motivated to make a new definition. And it's perhaps an odd sounding term, but I think it's not too bad. We're going to define a vatrix with a V to be a matrix whose entries are all vectors. And we're going to agree that the vectors are all of the same size. All right, so now instead of having matrix algebra, we can consider vatrix algebra. We can take linear combinations of vatrices if their entries are the same size. And more importantly, we can multiply a vatrix by a matrix of numbers. So for example, the kind of thing that we're actually interested in is a vatrix whose entries are basis vectors. So here are the vectors E1 and E2 from Bob's basis. And we can put them together in a matrix, actually in a vector, but it's a matrix, and we can call that B. So this object here is actually something new. It's actually a vatrix because it looks like a matrix, but its entries are themselves vectors. And correspondingly, Rachel's basis gets expressed in terms of this vatrix, the vatrix F1, F2. So these are two matrices of the same size. So one thing we could do with them is we could add them if we wanted to. So B plus R would be the new matrix E1 plus F1, E2 plus F2. But more pertinent to the direction that we're going in, what we can do is we can express a relation between the two basis vectors by this equation involving the ordinary matrix 3, 1, 1, 2 and these matrices R and B. So F1, F2 is equal to 3, 1, 1, 2 times E1, E2. That's a matrix equation. And if we wanted to invert that and express the matrix B in terms of the matrix R, we would get this. We'd have to use the inverse of this matrix, which is 1 over 5, 2 minus 1 minus 1, 3. That would express the relation between the Rachel's vectors over here and Bob's vectors over here. Here we had Bob's vectors on this side and Rachel's vectors on this side. Okay, so the advantage in introducing these matrices is that it allows us to encode the relationship between two bases in a nice compact matrix form. This is very useful. So now let's talk about coordinate vectors. We're going to stick with Bob and Rachel here, and we're going to stick with this vector v, which we said was 10, 8. And we saw that we could express it in terms of Bob's basis vectors E1, E2 as the combination 7 times E1 plus 4 times E2. And I remind you that E1 and E2 in this equation are vectors. Now the point is that we can now express this linear combination in a matrix or matrix form. We can rewrite this now as the vector 7, 4 multiplied by the matrix E1, E2. Because this is just a row vector times a column vector, if you like, and it's 7 times E1 plus 4 times E2. That's exactly the same. So this is the matrix that we called B, that represents Bob's system. And this vector here now is what we're going to call the coordinate vector of the vector v that we're starting with respect to the basis B. So we're starting with the vector v, then this vector 7, 4 is the coordinate vector of v with respect to b, and we'll write it this way, v sub b. Notice that it's a row vector. That row vector times that column vector of the basis. And so we can rewrite that in this rather short form, that the vector v is equal to the coordinate vector of v with respect to b, v sub b, times the matrix B. And you should think of this as being some kind of abbreviated form of this. It's a coordinate times like a vector. That's the coefficient and that's the vector. Except it's a vector of vectors. Alright, that was all with respect to Bob's point of view. The same vector, v, can also be expressed with respect to Rachel's basis, as we've seen as 2f1 plus f2. Okay, so correspondingly, we can write it as the vector 2, 1 times the matrix f1, f2. This is then the coordinate vector of v with respect to r. And this is what we called R, the matrix R, which encodes Rachel's basis. Its entries are exactly the vectors in Rachel's basis. So we get v equals v sub r times r. So the same vector can be expressed in terms of Bob's basis this way and in terms of Rachel's basis this way. So the basic setup is that we have a vector, like v, is the product of a coefficient vector, like v sub b or v sub r, times a basis matrix, like b or r. Coefficient times vector. Okay, so now let's have a look at how a change of basis is interpreted in this language involving matrices. So we'll look at change of basis, the relationship between two different bases, and we're going to stick with our example of Bob and Rachel's systems. So suppose we have a relation between Rachel's basis and Bob's basis expressed in a matrix form involving some matrix C. In our example, C happens to be 3, 1, 1, 2. And I remind you that the relationship is that F1, F2 equals 3, 1, 1, 2 times E1, E2. That's the example that this is encoding. Now let's look at the two expressions that we derived on the previous slide for a general vector V. So we saw that a general vector V can be expressed in terms of Rachel's system as a coefficient vector, V sub r, times the matrix R, this one here. Now this matrix R, we've said, is C times the matrix B. So in this equation we can replace the R with C times B. Now actually there's brackets around here, but this matrix operation, even when extended to matrices, is still associative. So in fact we don't really need brackets there. And if we think about it then in terms of the same vector expressed in terms of Bob's system, V sub B times B, then by staring at these two things here we see that the V sub B has got to be V sub R times C. Because this times the matrix B equals this times the matrix B. So V sub B equals V sub R times C. This is a relationship between the coefficient vectors of the vector V, which is arbitrary, in Bob's system and in Rachel's system. So have a look at these two equations. They're intimately connected. They're basically equivalent. This is a connection between the bases vectors themselves, expressed in terms of matrices, and this is the corresponding relation between the coefficient vectors. Notice that here the C and the B are together and the R is by itself, and that here the R and the C are on one side and the B is on the other side. So let's have a look at the special case where we've been talking about. So V is equal to 10, 8. R is equal to C times B. That's the equation right there. There's R, there's B, and there's C. And this expression here that we were writing down is just the relation, in this case, that the V sub B is the coordinate vector with respect to Bob, V sub R is the coordinate vector with respect to Rachel, and yes indeed 7, 4 equals 2, 1 times C. So note the same C, that matrix there, is appearing in both equations, but it's appearing first on the left on this side and on the right on this side. C is our change of basis matrix. That tells us how to go from Bob's matrix to Rachel's matrix, or it tells us how to go from Rachel's coefficient vector to Bob's coefficient vector for a particular vector V. So it plays this sort of dual role. There are these two ways of thinking about what the change of basis matrix is doing. It's acting either on matrices or it's acting on coefficient vectors. So I'd like to alert you to the fact that we are changing notation slightly here in this new framework from a previous lecture. In a previous lecture we talked about coefficient vector of a vector with respect to a basis in terms of a column vector. We are now changing our point of view and thinking of a coordinate vector as a row vector. Alright, so also observe, as we've done before, that a change of basis matrix C plays sort of opposite roles on coordinate vectors and basis matrices. So here are the same relations on the previous slide. I'm just copying them again. We have R equals C times B, and then V sub B equals V sub R times C. The same change of basis matrix C. So we're going to introduce a little bit of notation for C to tell us what it's actually doing. It's a relation between the two systems or bases R and B. And our convention is that in this case here we're going to say that this matrix C that's appearing is C sub R comma B. So if we plug that notation into both of these equations, this one reads R equals C sub R comma B times B. And this one reads v sub b equals v sub r times cr comma b. Okay, let's look at these two equations. So notice in this one here that involves matrices, the b and the b here are together. So you can kind of think of them as canceling. The b and the b are kind of together, they cancel, and we're left with the r. The same thing is happening on this side, except that now the c is on the right-hand side. But still this r and this r are sort of adjacent, and if you think of them as sort of canceling, then we're left with a b. So if you think of this sort of business of adjacent b's canceling or adjacent r's canceling, then it makes it easier to remember both of these equations. So r equals c sub r comma b times b, or v sub b equals v sub r times c r comma b. So there's a two-way interpretation. This change of basis matrix tells us how to convert a coefficient vector with respect to r into a coefficient vector with respect to b. On the other hand, it also tells us how to convert the basis b to the basis r. If we do want to go the other way around, if we want to express the basis b in terms of the basis r, or the coefficient vector v sub r in terms of the coefficient vector v sub b, we have to multiply both of these equations by a C inverse. A C inverse to the right on this equation and a C inverse to the left on this equation. And the inverse is just going to be given by interchanging the indices b and r. So C sub b comma r is just C sub r comma b inverse. So we're going to call C sub r comma b, that's a change of basis matrix. And that's our notation that we're going to use, and I think it's quite consistent and somewhat elegant. Alright, so here's an exercise for you to solidify your understanding and also to suggest how we can go a little bit further and introduce a third basis into the story. So in that diagram of Rachel and Bob's basis vectors that I drew, we were actually looking at both of them from our own point of view. The framework that we drew with our coordinate axes was different from both Bob and Rachel's systems. We can incorporate that by thinking about our basis vectors, say G1 and G2, as introducing a third matrix. Let's say capital O for our. So in our system, G1 is 1, 0. It's just the basis vector in our little space. And G2 is the vertical basis vector 0, 1. So that's also a matrix. And so we have three matrices actually around. We have ours, Bob's, and Rachel's. So we've talked about the change of basis matrix from Bob to Rachel, or from Rachel to Bob. So now we can also talk about the change of basis from our to Bob, or from Bob to ours, or from ours to Rachel, or from Rachel to ours. So maybe you'd like to think about how you write down those matrices. And you can verify that the change of basis from ours to Rachel's times the change of basis from Rachel's to Bob's equals the change of basis from ours to Bob's. And then you can explain why this kind of equation holds more generally, not just for these three particular bases, but more generally. And here, just an exercise to find the vector v if we know its coefficient vector in Bob's basis, happens to be that one, or maybe we know its coefficient vector in Rachel's basis, might happen to be that one, or in our basis happens to be that one. Now let's apply what we've learned to this rather interesting application of Taylor coefficient vectors for polynomials. So we're moving into the calculus side of things and applying this linear algebra to shed some interesting light on an important aspect of calculus, which is often not treated very thoroughly in calculus texts and courses in calculus. So we look at Taylor coefficient vectors from this linear algebraic point of view. And to be very specific, we're going to stick with our familiar space P3 of polynomials of degree 3 or less. So these are polynomials of the form a plus b alpha plus c alpha squared plus d alpha cubed. That's a four-dimensional space of polynomials. And we've seen that it has many bases. We've talked about all kinds of different bases of this space. Today we're going to look at a particular family of bases associated with the Taylor coefficient idea in calculus. So we're going to now also organize these different ordered bases by writing the associated matrices. We now have this notation that allows us to compactly express a basis by just writing down a matrix. Alright, the most familiar and standard basis of this space is the basis consisting of the polynomials 1, alpha, alpha squared, alpha cubed. That's sort of implicit when we write down this expression. We're writing P as a linear combination of 1, alpha, alpha squared, and alpha cubed. So that's a basis, and we're going to give it a name. Actually, we're going to give a name to the associated matrix. So there's a matrix. It's a vector, but its entries are themselves elements from this space, from this linear space or vector space. All right, so these things are not numbers now. These objects, these entries are polynomials. Or if you like, they're elements in this vector space or linear space. Now that's only one possible basis. We could also shift to looking at a polynomial from the point of view of the point 1. When we do that, then we can consider a new basis, the basis of powers of alpha minus 1. 1, alpha minus 1, alpha minus 1 squared, alpha minus 1 cubed. These are four different polynomials. They also form a basis of P3. We're going to call this matrix B sub 1. And we can do this not just for the point 1, we can also do it for the point 2, or the point 3, or the point minus 5, or the point 27 over 5. So we can do it for a general rational number C. And so let's introduce B sub C. This is the matrix formed by the basis 1, alpha minus c squared, and alpha minus c cubed. This is the Taylor basis associated to the point C on the line. And for us, the line is always rational numbers, so that's what we're dealing with here. So these are special cases. This is the general formula. There's really such a Taylor basis for every point on the line. There's a whole family of these Taylor bases. And we're interested in how they connect with each other because we'd like to go from information about a polynomial at one point to information about that same polynomial at some other point. Not necessarily from 0 to 1, but maybe from 2 to 7. So let's now use the framework that we've established with matrices to write an arbitrary polynomial in P3 as a product of a Taylor coefficient vector and a Taylor basis matrix. So for example, the polynomial 1 plus 2 alpha plus alpha squared minus alpha cubed, which actually appeared in our last lecture on cubic splines, we can now write this polynomial as the product of a coefficient vector times a matrix, actually a Taylor basis, expressed as a matrix. This is 1 times 1 plus 2 times alpha plus 1 times alpha squared minus 1 times alpha cubed. That's a matrix kind of way of writing that linear combination. And compactly, what we have here is this coefficient vector, and we're going to write P with brackets sub 0. So P sub 0, that's that coefficient vector, and this matrix, this column vector of basis elements, that's our Taylor basis B sub 0. So our polynomial p can be written as p sub 0 times b sub 0. That's the coefficient vector, or Taylor coefficient vector to be precise in this context, times this matrix, or this Taylor basis. So this is a linear algebra point of view on expressing this polynomial in terms of that particular basis at 0. Notice that we're compacting our notation a little bit. Probably we should write p with a b sub 0 down here as the index to be consistent with what we did before. But we're going to be a little bit more compact and just write p sub 0. Okay, the same polynomial can be expressed using other Taylor bases. For example, if we're interested in expressing it as a linear combination of 1, alpha minus 1 squared, and alpha minus 1 cubed, then actually in our previous lecture we saw that the coefficients were 3, 1, minus 2, and minus 1. So we can say that by saying that the same polynomial is the product of this coefficient vector times this matrix of basis vectors. And this coefficient vector, its name is p sub 1 because it's the Taylor coefficient vector at the point 1. And this basis, this Taylor basis, is what we're calling b sub 1. It's the powers of alpha minus 1. So for our second exercise, please express that same polynomial, which is 1, 2, 1, minus 1, b0, in terms of the Taylor basis at 2, also in terms of the Taylor basis at 3, and more generally, see if you can write down an expression for it in terms of the Taylor basis at a general point C. All right, now let's have a look at this interesting question of what are the relations between different Taylor coefficient vectors. Well, this is equivalent to finding relations between Taylor basis matrices. And for that, there's really one computation which is all important, and that's this one right here. And it's really nothing more, nothing less than the binomial theorem, expressed in vector form. So on this side here, we have powers of alpha plus c. It's just a little bit easier to use alpha plus c rather than alpha minus c. Because then we don't have minus signs, but we'll see shortly that replacing c with minus c doesn't change things very much. So let's have a look at how you express, say, alpha plus c squared. Well, that's just a question of expanding this out as a linear combination of powers of alpha. So alpha plus c squared is c squared plus 2c alpha plus alpha squared. And notice I've rewritten it in terms of increasing powers of alpha. Alpha plus c is just c plus alpha, and 1 is just 1. Alpha plus c cubed is c cubed plus 3c squared alpha plus 3c alpha squared plus alpha cubed. And if we wanted to go further to higher dimensional things, well, the next one would be alpha plus c to the fourth, and we would have to use the fourth row of the Pascal theorem. Now let's rewrite this in terms of a matrix equation. Okay, this is a vector, but we can write it as a matrix times the vector 1 alpha alpha squared alpha cubed. Actually, this is not so much a vector as it is a matrix, isn't it? Because the entries here are actually polynomials now. We're thinking of alpha and alpha squared and alpha cubed as being polynomials in this space P3. And please check that this is, in fact, the matrix. So the first entry is this row times this column, which is just 1. The next entry, this row times this column, which is c plus alpha. The next entry, c squared plus 2c alpha plus alpha squared. And the last entry down here is c cubed plus 3c squared alpha plus 3c alpha squared plus alpha cubed. So that's how we go from the Taylor basis at 0 to the Taylor basis actually at minus c. We multiply by this matrix. And we're going to give this matrix a name. We're going to call it a generalized Pascal matrix. We're going to call it P, capital P, sub C. And it's a generalization of the Pascal matrix that we saw in our cubic spline discussion in our previous slide. There we were only looking at the case when C equals 1. So if C equals 1, then this reduces to what we call the Pascal matrix P, or P sub 1. There's a 1 here, a 2 here, a 3 here then. There'll be a 1 here and a 3 there and a 1 here. So a column of 1s, a column of 0, 1, 2, 3, and a column of 0, 0, 1, 3, and 0, 0, 0, 1. So this is a generalization. It's the generalized Pascal matrix P sub C. There it is right there. It's actually an interesting and important matrix. It tells us how to change basis from this basis to this basis. Now let me make some variants. Suppose that we wanted to replace C with minus C. So this would be alpha minus C squared, alpha minus C cubed. Then what would change here is that this matrix would be P of minus C. The C would be replaced with minus sign. So there would be a minus appearing on this sort of subdiagonal here. This subdiagonal wouldn't change because the C squared doesn't change if you replace C with minus C. But this one here would also get replaced with minus. Right? So minuses would appear there and minuses would appear there. Let me make another observation having to do this, another variant of this. Suppose that we wanted to relate not these two bases, but a little bit more general. Suppose we wanted to replace this over here with alpha plus D, let us say. So if we replace alpha with alpha plus D, then this would be alpha plus D squared, alpha plus D cubed. And then over here we would have alpha plus D plus C all squared, and alpha plus D plus C all cubed. So the relationship between the Taylor basis at minus D and minus D minus C is still multiplying by the same generalized Pascal matrix P sub C. This is a very basic but important equation. It really encodes a fair amount of calculus in it. There's actually a fair amount of calculus in this simple application of the binomial theorem. The binomial theorem is very, very important in calculus. It's a central building block for calculus. So let's summarize that definition here more formally. So the matrix capital P sub C is this matrix right here. We're going to call that the generalized Pascal matrix. And we've just seen, what we've established is that B sub minus C, that Taylor basis matrix, equals capital P sub C times B sub 0, the Taylor basis matrix at 0. So this is the change of basis matrix that goes from the Taylor basis at 0 to the Taylor basis at minus C. Well, equivalently, if we're interested in coordinate vectors and not in actual basis matrices, then the P sub C ends up not on the left-hand side but on the right-hand side. And we can say that if we have a general polynomial little p, then its coefficient vector at minus C times this change of coordinate matrix P sub C equals the Taylor coefficient vector at 0. So these two things are equivalent in the way that we've already looked at several times. Okay, so now there's some interesting exercises that I'm now going to leave you with, since this is the last lecture of this first half of the course. So we have some interesting exercises now to allow you to investigate more fully the interesting structure behind here. So these equations and a generalization already encode a lot of powerful information about how to relate Taylor coefficients from one point to another. It's essentially this formula here. So the first exercise is to show that these generalized Pascal matrices have an interesting arithmetical properties. That if you take P sub C and P sub D and you multiply them in either order, you get P sub C plus D. That if you replace C with 0, you just get the identity matrix. And that if you want the inverse of P sub C is P sub minus C. This makes this what's called a one-parameter group of transformations. That's a very important kind of algebraic structure in the space of matrices. Your next exercise is to prove a very important generalization of the formula on the previous slide. We're going to call that the Taylor vector translation theorem, or maybe a little bit longer, Taylor coefficient vector translation theorem. It tells us that for any polynomial p in P3 and any rational numbers c and d, if you look at the Taylor coefficient vector at D and you multiply it by the generalized Pascal matrix P sub C, then you get the Taylor coefficient vector at D plus C. So we saw this special case when D equals minus C. And to prove this as a hint, you can go back to that fundamental equation relating the powers of alpha plus C and the powers of alpha and replace alpha with, say, alpha plus D as I suggested when I was talking about that. All right. So this is a very important thing, and you will probably have deduced this already if you did the exercises from the previous lecture on the cubic splines. You will have realized perhaps how to go from the Taylor coefficient vector at one point to the Taylor coefficient vector at another point. And then our final exercise is to connect this a little bit with calculus. For those of you who have done calculus, if you haven't done any calculus, don't worry. This connects with the Math Foundation series where I'm slowly introducing an algebraic form of calculus. In particular, Math Foundation 70, I talk about subderivatives and things like that. So I just want to connect here that if we think of this Taylor coefficient vector, P sub C, in terms of the entries as depending on C, okay, then these four entries end up being the original polynomial itself, the first derivative, the second derivative divided by 2, and the third derivative divided by 6. And these four quantities, I prefer to call them subderivatives. So they're a lot like derivatives, except that they're a little bit normalized to make them a little bit nicer. And this is a very nice approach to calculus. So basically what we're seeing here is that all of these first four derivatives, including the function itself, are already encoded in translation of coordinate vectors. We're just really translating the polynomial and seeing what happens to the Taylor coefficient vectors. So it's a powerful approach to calculus which is encoded essentially in an exercise like this. Alright, so this is now the end of this first half of this course on linear algebra. If you've come all this way and you've mastered most of the material, congratulations, you've done a lot of work. You have learnt a lot of mathematics. Some of it's a little bit new, but I think it's a very nice approach to linear algebra, emphasizing the geometry and applications. In our next half of the course, which is going to be starting soon, we're going to go in some additional new directions, and we're going to solidify some of the understanding that we've gained already. In particular, we want to extend linear algebra to apply it to geometry. Linear algebra is a very important and powerful tool to tackle geometrical issues. And we're going to do that. We're also going to look at other applications, maybe to economics, to engineering, and so on. We're going to look at matrix algebra a little bit more thoroughly. There's a lot of beautiful things just having to do with the algebra of matrices. And we're going to have to say some more about eigenvalues and eigenvectors, which is actually a little bit of a shaky issue. Okay, so lots to do. Make sure that this first half of this course is well under your belt. So if necessary, go through the lectures again. If you're teaching a course, then this is a good place to stop and have a semester break. I'm shortly going to post some notes that support this first half of the course somewhere, probably on the WildEgg site, and there you'll be able to download PDFs for the various lectures that I've done so far. These PDFs are really just pictures of the slides, so but at least gives you some kind of idea, a quick reference of what we are doing at what point in every lecture. All right, so next time we are going to be introducing part 2 of this first course in linear algebra. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.